Wrinkles may look like simple creases to the naked eye, but under the microscope, they're far more nuanced and surprisingly political. Some form like whispered lines after years of expressive smiles or squints. Others deepen with age like the fault lines of a tectonic shift, accompanied by thinning skin and the collapse of support structures. But here's the cellular punchline. Not all wrinkles are created by the same kind of damage, and not all damage is caused by the same kind of senescent fibroblast. In fact, mounting evidence suggests that specific subtypes of senescent fibroblasts may drive different patterns of skin aging, from fine lines to sagging folds to uneven tone, and understanding that could radically change how we treat them. At the heart of it is the collagen-producing fibroblast, the cell most responsible for your skin's firmness, bounce, and youthful tension. In youth, dermal fibroblasts work in elegant coordination to synthesize types I and III collagen, weave a tidy extracellular matrix, and communicate with neighboring cells like keratinocytes and immune regulators. But as fibroblasts age, or experience stress from UV, pollution, oxidative damage, or mechanical wear, they begin to senesce. They stop dividing, lose their precision, and most importantly, start to secrete a potent SASP, senescence-associated secretory phenotype, that includes collagen-degrading enzymes like MMP-1, MMP-3, and MMP-9. But the real twist is this: senescent fibroblasts are not a single species. With the rise of single-cell RNA sequencing and spatial transcriptomics, researchers are discovering multiple fibroblast subpopulations that age and senesce in different ways and contribute to distinct visible outcomes on the skin surface. For example, one subtype, let's call them matrix degraders, tends to congregate in deeper dermal layers and express high levels of matrix metalloproteinases. These cells are specialists in collagen breakdown, particularly during prolonged UV exposure or oxidative stress. They're highly active in areas that experience structural collapse, sagging cheeks, thinning neck skin, and the flattening of once rounded contours. These are just wrinkles, they're signs of volume loss, and they correlate strongly with fibroblasts that have flipped into a senescent, degradative state. A second group, inflammatory senescent fibroblasts, tends to hang out near blood vessels and hair follicles and produces a SASP rich in IL-6, IL-8, and TNFA. These cells don't necessarily degrade collagen directly, but they attract immune cells, promote low-level inflammation, and interfere with repair signals from keratinocytes and stem cells. They're often linked to skin that appears dull, uneven, or inflamed. Think persistent redness, broken capillaries, or a loss of glow that doesn't quite qualify as a wrinkle, but feels like aging all the same. Then there are fibrotic senescent fibroblasts, which, paradoxically, overproduce abnormal collagen and ECM components, often leading to stiffness or poor skin recoil. These may underlie the kind of rough, leathery texture found in chronically sun-exposed skin, where the matrix isn't destroyed so much as it's distorted beyond usefulness. These cells tend to express fibrotic genes like TGF, SET1, COL5A1, and LOX, and they can actively block regenerative signals that would otherwise recruit fresh, youthful fibroblasts into the area. Finally, quiescent-like senescent fibroblasts exist in a kind of limbo. They're not producing high SASP levels, and they're not killing collagen, but they've stopped responding to regenerative cues. They're often found in older skin that looks tired, more than damaged. The result? Fine lines, loss of elasticity, and an increasing resistance to interventions like microneedling or topical retinoids. These fibroblasts aren't inflammatory, but they act as roadblocks to renewal, and they're often found in skin that doesn't bounce back the way it used to. So when it comes to wrinkles, sagging, and skin tone, the aging process isn't just one long march of degradation. It's a mosaic of different senescent programs, each contributing to specific features of visible aging. That means the future of anti-aging therapies won't just be about collagen creams or laser treatments. It will require targeting the right senescent subtype in the right location. Imagine a diagnostic tool that uses skin imaging and AI-driven transcriptomic analysis to map the senescent subtypes across your face. Your crow's feet might show a dominance of matrix-degrading senescent fibroblasts, best treated with senolytics or peptide-based MMP inhibitors. Meanwhile, your dull cheeks might be inflamed by SASP-heavy fibroblasts, better addressed by xenomorphics or anti-inflammatory polyphenol. Your jawline sag? Maybe it's the fibrotic subtype holding on too tight, responding best to mechanical stimulation, retinoids, or ECM-modulating compounds. Even cosmetic interventions like fillers or microneedling could be personalized based on senescence mapping. Targeted senescence clearance before treatment could prime the tissue for better results, while post-treatment senescence modulation might extend benefits or reduce side effects. In short, not all wrinkles are the same, not in appearance, not in origin, and definitely not in their underlying biology. Aging skin is a composite of senescent subtypes with unique secretions, behaviors, and repair resistance. But once we learn to decode this cellular language, wrinkle by wrinkle, the future of skin rejuvenation won't just be younger, it'll be smarter.